Okay, so since you were deprived from bijection this morning, I want to start this sixth lecture by showing still one bijection. So this will be a part 3 in my 5th lecture, and it will be just one bijection. So certainly for many of you know this bijection already, and this will be not very interesting. But for the others, I can't show nice formulae for the number of maps without telling you that they have been explained combinatorially, and by this I mean bijectively. So this is essentially, well, one of the early bijections in the topic. So let me remind you that we had proved that the number m of n of maps, planar maps with n edges, this number has a nice expression. There's a factor 2, then there's a 3 to the n, then there's 2 linear factors at the denominator, and then there's a binomial coefficient. So this was proved by Tutt in the 60s. And this can also be written times Cn with Cn. So that's the number of plane trees that we had this morning, but it also counts so binary trees with n inner nodes. So these binary trees, they are things like that. So every vertex has either 2 children, so now they are drawn that way, has either 2 children or 0. Okay, so that's a binary tree, and the inner nodes are those ones. Okay, so question, could we explain this formula combinatorially? That is, can we take a tree and do something in 2 times 3 to the n ways and obtain n plus 2 times every map of size n? And the answer is yes, but it took some years before explanations of that type were found. So in the 80s, you had a first bijection, in fact, not exactly with those trees, by Henri and Vauquelin, which has been better described in clearer terms later by Gilles Schaeffer. But the one I want to describe is of a different nature, and it was described again by Gilles Schaeffer in his thesis in the 90s, and in fact for more general maps, but I'll stick to this one. Okay, so the first thing that we should do is to realize that maps with n edges are in bijection with 4 valent maps with n vertices, and that's a very simple bijection. So let me take a map. Okay, so here's my map. By 4 valent, I mean that every vertex has degree 4. So from this map, which has 1, 2, 3, 4, 5, 6, 7 edges, I should build a 4 valent map with n vertices. It's not rooted. It will be. There we are. Thank you. All my maps are rooted. So what do? I first create one vertex of the new map per edge of the original one. So in red, and I put in the middle of every edge. I put a vertex in the middle of every edge. And then I need edges in this new map. And what I do is that I take every face of the original map and walk around it, just joining consecutive vertices. So that's for this face. That one. Here I should be a bit careful, so say I walk here. And then there's the outer face, which I shouldn't forget. And say if I want to keep the same, no, okay, let's do it that way. And then what should I choose for the new root corner? Say I will move the root corner to the former root edge, to the root edge of the original map. Sorry? So 4 valent here means that every vertex has degree 4. And the reason for that, so you have one edge in the original map, the corresponding vertex of what I claim to be a 4 valent map, and so you have one face on each side. It could be the same face, and so you have these paths inside faces. They create 2 half edges on each side of the edge. Okay, so this means that counting maps by edges is equivalent to counting 4 valent maps by vertices. Okay, so maybe we are in good shape. Well, here in a binary tree, everything is 3 valent. So if we start from a binary tree, we should somehow add 1 incidence to every vertex to get something that's 4 regular.
Sorry, can you show me quickly reverse of this projection?
Oh yeah, that's a good point. So you start from your 4 valent map. So it's 4 valent, so it's Eulerian, so meaning that you can bicolor the faces, black and white, say. And so, well, sorry, I'm not doing the right thing. You just triangulate every face. So you see if you start, so if you look at this red face, you triangulate the black faces. So you have 2 types of faces. So by convention, what should I say about the outer face? So let's say it's red. And so all faces that were corresponding to a former face here become red. Yes. So that's the ones, so that's every other face. So there's now my outer face here. And that's it. Yes. Okay, and so if I want to go backwards, I take the other faces, the ones that I have not dashed. I put a vertex somewhere in those faces, and I triangulate. Yeah, yeah, it was a good question, of course. Okay, so now I'll start from a 4 valent map. So maybe I should stick to my example. Oh, no, I won't. So how does a 4 valent map look like? Well, like this. What should I take? No, maybe I should stick to my example. So what did I want here? I insisted that I wanted a loop. So that's already degree 3. I'll get there at some point. Now I'm not sure which picture I should look at. It's rather worrying. I've written raté. So what is exactly my example? Okay, so here I have a diagon with a loop inside. Then I had something going here. A big thing here. Here I have this little square with a duplicated edge. And where did I have my root? Somewhere here. Is this 4-valent by any chance? Okay, so let's say this is my example. Okay, and I want to build a tree from that. So the difference between maps and trees is that a tree has a single face and a map may have several faces. So what I want to do is to take this and open some edges, cut them into 2 half edges to create fewer and fewer faces until I get a single face, hence a tree. So what the recipe is as follows. So you walk around the map. Say in a counterclockwise order, starting from the root. So you will walk along edges, and after visiting each edge, you ask what happens if I open this edge into 2 small half edges. Will this disconnect the map? And so you open, and we'll see what this means. Every edge if this is not good English, but I apologize for that. If this does not disconnect the map. Sorry? Yeah, so it's an incremental construction that is, well, you'll see, I should probably do it. Okay, so you start, say, here at the root corner, and you walk around the map. So the first move I'm doing is walking along this edge here. And can I open it, that is, erase the central part? If I do this, do I get something that's still connected? Yes. Okay, so I declare that I open this edge into 2 half edges. The first one I will call, say, a bud. And the other one I will leave like that, and I will call a leaf. Okay. So this becomes if I was walking like that, this will become a bud and a leaf. Okay, so I've walked here and I've reached these points. So I go on walking now the map with the legs that I have. So I walk along this edge. If I open it, will I get something connected? Yes. So I do open it, creating a bud and a leaf. And I've reached this corner here. So I go on walking around my structure. I come here. Can I open this thing? No, because if I open this piece will fall out. So I keep this one, and I'm here. Now I walk, so maybe I should take the corner here. I walk here and reach this corner. Can I open this edge here? No, because I would get two pieces, so I go on walking here. So I go on. So I walk on this edge, which I can open. So I do open it, creating a bud. So the first half edge becomes a bud, the other becomes a leaf. So I've reached this root corner. I go on walking here around. So now this is open, so I can enter what used to be a face. So I do. I reach this corner here. And here I meet a new edge, which I can open. I do that. I've reached this corner. This is my next edge. And I can open it. I'm here. Can I open this next edge? Yeah. And I've reached this corner here. This edge I had already visited and decided not to open because it was an isthmus, so it's still an isthmus, of course, now. I've just opened more faces. So I get around the leaf. Here I enter this face, and I meet for the first time this loop, so loops can always be opened. I read this corner, and is there still something that I need to open? So this is where it gets complicated. Okay, so I will end after having gone around. There's still this face, and I think, if I'm not mistaken, I meet this edge first, hopefully. This is confirmed. Uh-huh. Really? Ah, bad luck. So where did I come? Where did I arrive?
The other way around.
Okay, I believe you. I will not be able to reconstruct. So you're telling me that the bud is here and the leaf is here. Okay, thank you. Okay, so at the end of my journey around the map and around the open or the partially open map, I've reached some.
Do a full turn without opening.
Yeah. So I've got something which has a single face and that is connected. So it's a tree, which I'm going to draw in a more tree-like fashion. So I still have my root corner. This is very convenient. So how does this tree look like? So I have, okay, a vertex. The root corner is here, And then I have a leaf, something with a vertex here, a bud, then another bud, which was this one. Then I follow this edge. I first see a bud. Here I have two normal vertices. This one has first a leaf, another leaf, and a bud. So I'm here. This one has first a leaf, then a bud, then a neighbor, and here I have a leaf, another vertex, and a bud. So I've reached this vertex hanging, which has this parent. So I find leaf, bud, vertex, leaf, bud, vertex. And this is the vertex which has bud, leaf, leaf. Okay, it's a rather thin tree, but this need not be the case. And maybe one remark is that in a four-valent map, you cannot have an isthmus. You cannot have a bridge. If you count the parity of the degrees, in particular, the root edge can never be a bridge, which means that it will always be open. And so, in particular, I will decide to hang so this is what you see here. The first edge was open. So I will decide to draw it a bit differently. I will just hang it by this bud that used to be the beginning of the root edge. Okay, so what did I get? So I got a tree. And then it has a number of properties. So it has n nodes. So every vertex of the map has become a node of the tree. It has remained four-valent because I have just erased the center of every edge, but all half edges have been preserved. And then it's not very hard to see that every node, so it's incident to four half edges, and in fact one of them is a bud, with the exception of the root vertex, which has two buds. Okay, so this is not all. There's one more property. I have a bud. That's a good question. So it used to be adjacent to a number of faces. And so you create this bud. I guess the first time, the first or last time you open a face incident. So at some point you'll visit, so you have your node with possibly several faces. And there is a first time where you visit, say, this corner, And at this point, you create a bud to get big. It's related to the fact that there's no isthmuses, so you always have something to open at every node. What is not clear for me at the moment is why there should be only one bud. But then if you count, you have to match the number of buds and leaves. And so it should come from that. I mean, I don't say that this is obvious. There's something to prove, but that's the properties of the tree that you obtain.
Only one bud.
Yeah, has exactly. Except the root, which has 2. Okay, so in other words, what I have here, if you forget the buds, it's one of these binary trees with n nodes. And then it's decorated by adding at each node one bud in each of the 3 possible. So in a binary tree, you would have something like that. And then what you do is that you add in one of the 3 possible corners a bud. So here you get a smell of the 3 to the n that we have in the formula. So if these were the only conditions, and if this was a bijection between those trees with buds and maps, you would get something like m of n is, I take a binary tree, and I have this decoration on every vertex. And this is not true, and the question is where does this factor come from? So the point is that here you do not get any tree. And to see why, so we'll try to work the bijection backwards from a tree to the map. So what you want to do backwards is walk around the tree and build faces, the faces that you have deleted, by joining a bud to a leaf when they are consecutive. So by this, I mean that you walk around the tree and you pay attention to the sequence of buds and leaves that you see. So that's a word on the alphabet BL. And when you see a sequence bud leaf, you match them. So that's a cyclic word. So for instance, here, I see bud, bud, leaf. OK, so I claim that they come from a face. Leaf, bud, leaf, bud, leaf, leaf, bud, bud, leaf. That was my loop. Leaf, bud, leaf. So then I have closed partially and reconstituted some of the faces. Leaf, bud, leaf. Ah. And bud leaf here. OK, and if I wanted to, well, I would match the root bud corresponding to the root edge of the map to the leaf. However, there are, so this, given that you have as many buds as leaves, you can always match these things. But the problem is that in some cases, and these are the cases that you don't want, so you have your tree, and when you do this matching procedure, there's no reason why at some point you wouldn't say what may happen is that at some point you go around. No, I have it wrong. I want to avoid going above this half edge. So what could happen? the leaf. This one? Yes. Not really, because if I put it on the left, yeah, well, it will be matched by the root, but I don't want so. I don't want to have. I want this somehow to be the final edge. What I don't want to have is that a later edge goes around that way. So there's another way. So essentially, you've seen here that the last edge I could match was the root edge, the former root edge involving this root leaf. This is not very convincing, having a root leaf. And there's another way of describing that. Yeah.
What you need is that when you do this
matching procedure, yeah,
you never match the root edge, the root bud, until the end.
Yeah, so in other words, maybe when you match it, the face on the right is the infinite face. I think that's a better way of saying that. So there's another way of describing this same property. So my original tree looked like that, and then whatever. And I will redraw this by calling leaf this half edge. So formerly I had n buds and n leaves. And now I still have n n minus 1.
N plus 1 buds.
Yes, that should be the case. Yes. Yeah, you're right. So now I have just n buds and n plus 2 leaves. So I can perform the matching procedure here. And then the condition, if I'm not mistaken, means that, so at the end I should have 2 leaves left single. And the condition is equivalent to saying that no bud will match the root leaf. So what is now forbidden? So you see it's the same picture. So here, if I replace the root bud by a root leaf, then I don't want, in my matching, if I have this situation here, I would match the root leaf. And so the condition that you need is that this root leaf remains unmatched in this formalism. So you have now a tree with n buds, that is exactly 1 at every vertex, n plus 2 leaves, and including the root leaf. You do your matching procedure, bud leaf, and 2 leaves remain single, and you want the root leaf to be one of them. And such trees, so they are the ones that are in bijection using this construction, they are called balanced trees. And so these are the ones that are in bijections with the 4 valence maps. And so this is why the number of maps is not exactly 3 to the n times the number of binary trees. Okay, so now we need to understand why the number of balanced trees is just multiplied by 2 over n plus 2. Okay, so let me call B of n the number of those balanced trees with n nodes. And what I'll prove is that n plus 2 times B of n is 2, 3 to the n times the nth Catalan number. So that's just all trees with buds. And this is the number of balanced ones. And I recall that in those trees, this is the number of leaves. Okay, so let me start from the right. So you have one tree here, any tree. You can perform 1, 2, 3, 4, 1, 2. You can perform the matching procedure, and maybe it's not balanced, hence maybe the root leaf is matched with a bud, maybe it's not. And at the end, you're left with 2 single leaves. And what you do, so you have 2 single leaves, and you mark one of them. So these objects, trees with a marked single leaf, are counted by 2 times 3 to the n times Cn. And you want from this to build a balanced tree with a marked leaf. So do you see how you could do that? It's a kind of double rooting argument. So I recall that a balanced tree is one in which the root leaf is single in the matching procedure. So I want to start from this. Yeah. Yeah, and what?
The other and match leaf.
So I start from this, and I want to get something. I'm cheating with here a single leaf. Okay, now this is telling you what to do. So you take this tree, and you hang it by this marked single leaf. And the matching procedure that you had here will be exactly the same. So I had what? This, a bud, and a leaf. I had attached, but I've forgotten a leaf here. Okay, so I take this tree with a marked single leaf. I hang it by the leaf, and I mark what used to be the former root in red. So it has become now this. So I mark this leaf here. Okay, in both structures, you have 2 marked leaves. One here is the root, and here one is the other single, well, one of the single leaves. And here you have just one leaf marked, and the root is now single. So it's really a rotation of the tree, if you want. So Gilles was saying, when he found this, that in a sense, a map is a cyclic conjugacy class of a tree. So, or it's a tree taken up to rotation. Okay, and since B of n, that's the number of maps, then we are done.
Sorry, this process, are you changing the root?
Yes, precisely. So the root, the former root, is now a marked leaf. And the marked single leaf has become the root. So it's exactly a rerouting argument. I have a doubly rooted structure with two distinguished leaves that can actually be the same if this tree happens to be already balanced. And so I decide to root it here or there. So in other words, I'm rotating just a tree, in fact. Deciding,
so
yeah?
If your tree was with a different root, that you...
No, because I mark here, I mark the former root. So if it was rooted, and hence the n plus 2 here. So you get a balanced tree with a distinguished leaf. Yeah.
When you do that, you create a non-crossing partition. Buds and the leaves.
Yes, or a perfect matching.
By CN also. So could you take this as basis and add some parameters to reconstruct the whole structure? Start just from the and add some structure.
Not that I know right now, but maybe the bijections expert would tell you that this is the other. What do you think, Eric? Are there bijections that do what Philippe is asking for? That is the Catalan number is counted by the matching between buds and leaves, and then you interpret the 3 to the n differently? Yeah, is that? Yeah, so that's another. Okay, so I won't go really further with examples of bijections, but I want to tell you that this is the tip of some iceberg of wonderful bijections that explain formulae, explain why you have so many algebraic series, tree-like formulae, and things like that. So my original plan was to present for these 4 valent maps 2 bijections. So that's one with those trees with buds, which are sometimes called blossoming trees. So we've been from 4 valent maps to those trees with buds, which are sometimes called blossoming trees. But there's a different bijection, which in fact starts from quadrangulations instead, and which constructs labeled trees. So that's the original Corry-Vauquelin bijection, and then described in a better way by Gilles Schaeffer. So this is Schaeffer. And that's the one we've seen. So you have these 2 basic bijections, and each of them has a very rich descendants. So I can give some examples. So what Gilles actually did was for Eulerian maps in the origin. So that's maps with even faces. And then came the BDG group, so Jérémy Boutier, Philippe Di Francesco, Emmanuel Guiter, who built blossoming bijections for maps, even vertices. For maps counted by vertex degree, And then came still more bijections. Then with Gilles, we did that for bipartite maps. So you have black and white vertices, and for each color, you record the number of vertices of each degree. And in fact, this was equivalent to solving the Ising model on maps. And then more recently, you have some, so there were results on triangulations, quadrangulations. And then on the one hand, I think that Bernardi and Fusy, and then Marielle Bank and Dominique Poulalon. I always get the H at the wrong place, sorry. That's the second. So in both papers here, you have very general and generic bijections explaining, so here I skipped some, why essentially all the former bijections that were built for various subcases. And then the bijection with the labeled trees has a similar descendance. So for these, and in fact these, you have the so-called mobiles by the BDG group. And then you also have versions for higher genus, which I'm not sure exist here, with names like Marcus, Schaeffer-Gain, then Guillaume Chapuis, Jérémy Bettinelli. And you have also unified descriptions by Bernardi and Fusy. And in both cases, there's more. As I said, I'm not the expert, so I cannot tell you how you go if there is a one way to build one labeled bijection from a blossoming one. And no systematic way. I'm not sure what the experts would tell me. Eric? No? And one thing that I can tell you is that the ones you see the most often are the labeled ones, because they have a wonderful property, namely that when you get your label tree, the label that you have on a vertex is its distance to the root. So they are the ones that record distances, and they are the ones that open the way to the study of the convergence of random maps as a metric space, because the distance is recorded. Okay, and so this will be the end of my 5th lecture. And unless you have questions, we'll move to maps with something. And there will be, I promise, one more bijection by the end of this session. Okay, so that's lecture 6, I guess. So we want to now consider maps that carry some additional structure. And the first thing we're going to look at is maps with a distinguished spanning tree. So let me take a map. Rooted. And I call, say, S of n the number of maps, planar, rooted, with n edges, and a distinguished spanning tree. So for instance, here I could have, so for a spanning tree, I certainly need to take this edge. There's no loop in a tree, and so maybe I will take this and that. So a spanning tree is a tree that is a set of edges that covers all vertices. Okay? So there's a very classical way of counting these things, which was described by Malin in 1967. And in fact, you will realize that it's easier to count maps with a distinguished spanning tree than counting just all maps, even though the final series will not be an algebraic series. So this is essentially a bijection. So what we do is we walk this time around the tree, not around the map, but around the tree. So here I will do this walk. And each time I meet an edge, I cut an edge that is not in the tree, well, I will encode this in a way. So essentially, again, by a bud and a leaf, if you want. So here is my going around the tree. Okay, and I'm back. And I've cut this edge. So say I can use the same terminology. And I formed a bud and a leaf. Then I've cut this one. And finally, I've got the loop. So what do I get? I get a tree, which in my case is very simple. And then I have buds and leaves. Sorry. So here I have a leaf and a bud, which are these two. And then I also have a leaf here. And this was my root corner. Is this correct? 1, 2, 3, 1, 2, 3 could be okay. And now we are nearly there. And in fact, we're going to use something that essentially you asked for. So what do we have here? We have a tree, and at some point when walking around the tree, we insert a sequence of buds and leaves that should match. So another way of saying that is maybe now I can walk around the tree again. I can encode this. So when I see an edge of the tree, so the first time I visit it, I use, say, the letter A. When I get back, I use an A bar. And then when I meet a leaf or a bud, I use B and B bar. And so again, I have an underlying matching between the B and B bars. Oops, sorry. And there's also a matching between A and A bar, which correspond to just the usual encoding of a plain tree by a word on a two-letter alphabet. So in other words, what I have here is a shuffle of two words, in fact, of two dic words, if you know what a dic word is. One on the alphabet A bar, and the other on B bar. So by a shuffle, I mean that I have my two words, A bar, A bar, and then the other one, B bar, B bar. And I make from that a single word by shuffling the letters and just keeping the order of the A letters and of the B letters separately. So one example here could be A, then I put this B and maybe the B bar, A, B, A bar, and B bar. That's what I call a shuffle. Sorry?
Big words equals match.
Yeah, exactly. Yeah, you can. Sorry? Yeah. Yeah, so I don't claim that this word corresponds to this tree, sorry. So that's a good point. So here the word on my example would be, so I walk, I have A, then a B, then I'm back here, so that's an A bar, A, B bar, so that's a B bar. Maybe I should write it here directly. So that's a B for leaf. Here I have A bar, B bar, B, A bar, B bar. So here I had A, B, A bar, A. So my word is obtained cyclically by going around the tree. Another way of saying these dic words is encoding the A steps by up, the down steps by, the A letters by up, the A bar letters by down, and what I get is the so-called dic path. So a path that starts at level 0 and ends at level 0 and always remains non-negative. So this is the classical Catalan structure. Yeah. The size of the two words. Yeah, so they have to sum to n, because every edge is now either in the tree, if it was an internal edge, or it's been cut into a B and a B bar. So that's indeed a condition.
Sorry,
yeah.
Your example, I think it shouldn't be for A's.
No, there's as many A's as as edges in the spanning tree, and the b's as edges that are not in the spanning tree. So every edge in the tree, I will have an A, and in fact an A bar the second time I visit it. And for every edge that I cut, I have a B and a B bar, a bud and a leaf.
So if you translate it into a big path,
yeah.
Your example should go up, up, down.
So my example will be up, down, up, down, up, down. So here, so that's what I have here. So I go down each time I walk upwards. So here I have A bar, A bar, A bar for this tree.
But if you look at the translation you had on the left.
Yes.
Right, right, that one.
Yeah, so that's not finished.
Okay.
So, but it starts A bar. Yeah, then I'm sorry. Then I decided to draw it directly on the tree. So that's not finished. Yeah. Yes, you can. Yeah, yeah, you can. So essentially, you'll take your tree, and if you start from the word, maybe I could do that or try to. So I start from this word and want to build the corresponding tree with buds and leaves. So I read A, bud, leaf, A bar, I'm back here, A back, A bar, I'm back here, A, bud, A bar, leaf. So this is my tree, and the corresponding map is obtained by matching things like that. Yeah. In higher genus, so you should look at, well, if you want nice results, usually you would look at a map with a distinguished one-face map, not a tree. And then you do have a similar construction. No, well, I guess there can be results as well, but that's not, I'm not sure. So it remained to count things. So I started from n edges in my map and say I vertices. Or maybe I should say I plus 1 vertices. So this was the map. And so in the tree, I had I edges in the tree. Aline, you doubt? No? And so from this, so I got one word here. The A word has 2 I letters. And so that's a dig path or a parenthesis word. And so there's CI of them. And then I had the n minus I edges that were not in the tree. They have given rise to a word, a B word with 2 J letters in the B word. So that's a CJ. Okay, so now I'm taking the A word, the B word with the right length. So this fixes the number of edges and the number of vertices of the map with the spanning tree. And I still need to shuffle them. So there's an additional binomial coefficient. And so this gives you that S of n, the number of maps with n edges and the distinguished spanning tree, is the sum for all pairs I and j that sum to n. of Ci, Cj, and then you have to shuffle these two words. The total length is 2n, and you have to say, for instance, where you put the A word in those 2n places. So that's a formula, and in fact, this can be evaluated as the product of two consecutive Catalan numbers. So this is not hard to prove. And as you can see, this is rather simple to explain. So it's a tree or a shuffle of two trees. Another way of describing that is saying that you have your map, the tree, and you have a dual tree. If you take the edges that are the duals of the external edges, you take another tree, which is the one, so which here we have encoded by the B word, and it's the one that's counted by Cj. So a map with a spanning tree is just two trees that you have, in a sense, interleaved. And so that's really the structure. It's rather transparent, and it leads to this formula, which happens to have a nice closed expression. So some remarks. So first, so we have the associated generating function. So which is the sum of Cn plus 1, C to the n. And so it's a simple series with nice coefficient, but it's not an algebraic series. So I insisted on the fact that when we were counting maps with no structure, we were very often, almost always, in the world of algebraic series. This is no longer the case here. And one way of seeing that is by looking at the asymptotic behavior of these numbers. So we have 4 to the n for each Catalan number. So you have 4 to the 2n. There's some constant. And then each Catalan is n minus 3 halves. So you have n minus 3. And this cannot be the sum, if you think of, first of 4 to the n over n, so that's an expansion of a logarithm, which is not an algebraic series, and the same holds for this, which is a double primitive of something with a log, in a sense. So this implies that this is not algebraic. So still the numbers are very nice, and they satisfy a polynomial recurrence, a linear recurrence relation. So it's P recursive. And here, in fact, it's even an hypergeometric sequence. So that is Sn plus 1 over Sn is rational in n. So if you evaluate, well, this will be just Cn plus 2 over Cn, I guess. So that's very nice. So there's nice series that are not algebraic. And so this means that the corresponding generating function is what I call definite. That it satisfies a linear differential equation with polynomial coefficients. So I could even, if I find it, tell you what this is. So I won't copy it, but you have a linear dE differential equation of order 2. So this is our first example. So it's rather simple, but clearly we are moving away from the world of algebraic series. We are moving to a larger world of definite series. And since I had promised a second bijection, I want to show you a bijective proof of this formula. So far, we've proved bijectively the convolution formula, but I want to show you a nice bijection due to Olivier Bernardi, explaining directly the product formula Cn plus 1. I will copy my example. So remember, n is the number of edges. So here's my example. I have a map. I have a loop. And the spanning tree. So I should write the root corner here. And the spanning tree consists of those red edges. Okay? And I want out of these to form something, two objects that can be taken independently, one counted by Cn, the other counted by Cn plus 1. So the first thing I'll do is that I will orient every edge in the following way. So the edges of the tree, they are oriented away from the tree, from the root, sorry. Okay, so I go down in the tree. And then the other ones, when I walk around the tree, I want to meet them somehow in the wrong direction. So this one, the first time I meet them, when I cut them, I want to see first the end and around the tree I have this orientation. So the inner edges, they are oriented away from the root. And the external edges in a sense they are oriented towards the root. And so in total, I have n edges. And from this, I will form a tree, but not the same tree as before. Formerly, I had the spanning tree which had I edges. Now I want a tree with n edges. That is, I want every edge of this map to become an edge of the tree, of the new tree that I'm going to build. And then I'm going to build something else, which will be a non-crossing partition in this case, and which explains the other Catalan number. So first, the tree. So imagine that I have one vertex in this picture with a number of in and outgoing edges. So maybe in, out, in, and maybe out. I'm going to write this as a little blob, which is the vertex, with all its incident edges. But I'm going to group them in the following way. When I have one ingoing edge, then turning in this direction, I say that the following outgoing edge ends at the same point on the boundary of the blob. But then every time I have an ingoing edge, it will hit a new point on the blob. So in, there's no out, and here I have in and out. So let's do this for my tree here. So I have, so I'm drawing the vertices, which have become blobs. And one point is that I include this root corner, or this half edge, into my collection of ingoing edges here at the root bubble. Okay, so let me try to do this. So I have the root corner, then I have something outgoing, which will end somewhere here. And then I have another ingoing edge here coming from here. Okay, so at every vertex, I want to draw something like that. Okay, so now I move to this vertex. I have something in, then something going out, and then again out, going here. Then at this vertex, I have this ingoing edge, then out, then in, and then something that goes out here. So here I have in, out, and I should start paying attention to where I end here. Sorry, this is an ingoing here. And then I have, so this was this out. I have another one going out, and which is arriving here. Am I done? What should I do? No, it's in what you group is everything with one in edge. You have all the falling out. With this, just this, yeah, you're right, okay, thank you. I thought these two, but you're right, it's these two. Okay, so the little blobs, I dash them. Yeah.
Going away or toward the root, is it trivial that you or no, away from the root?
Sorry, which edge?
The idea that one edge, you point it away or toward the root.
Yes.
Is it trivial that you can always do that?
Yes, so essentially, it's related to what we were doing. So being away, going away from the root for all internal edges, that's fine. You just orient edges in a tree, going away from the roots. So for the red edges, that's OK.
No, I mean, for example, take the rightmost.
This one? No.
The rightmost, right.
Yes?
Why could it be going?
Oh, I decide of a certain orientation.
Oh, okay.
So I decide to orient internal edges away from the root that is going further from the point that's the closer to the root to the one that's further in the tree. Maybe I should insist on that.
No, okay.
So in other words, when I do what I was doing before, walking around the tree, so when I was doing an A, following an edge of the tree for the first time, I orient this edge in the direction where I'm going, whereas when I meet a B, I orient the edge towards the point where I am. OK, so here I claim that we have two pieces. So first, I claim we have a tree with n edges. And so the edges, they have been preserved. So what you have here, starting, well, I don't want to draw. But if you drop the blobs, what you have is a tree with n edges, with all edges oriented away from the root. So the idea is that when I was incoming here, so here I'm closer to the root than here. And so these are the descendants of this node at every blob. So there's something to prove here again, which I'm not going to prove. But you have a tree with n edges. So that's your Cn. So maybe I should try to draw the tree in a clearer way. So from the tree, so I have this little incoming edge here. So I draw the tree from here. So here I have a vertex, which has out degree 1. I reach this vertex at the top. Then I have, well, it has degree, it has 2 children. So let me go to this one. I have only one child. Then there's 2 things. This one here goes, so it's what? It's the first one here, goes up to something of degree 1, and the other one, am I lost? Sorry, so this was the thing of degree 2. The other one is just like this. And so here, this is this vertex, which has just degree 1. Do I have all the edges that I need? I started from 1, 2, 3, 4, 5, 6, 7, 8 edges. 1, 2, 3, 4, 5, 6, 7, 8 edges. OK, so this is the tree. And it has as many edges as the original map. And then I claim that the little blobs, they define a non-crossing partition on the nodes of this tree. And, well, it suffices to draw them again. So I have one part that contains this node and that node. So where are they?
All those nodes according to the path that you...
Yeah, so the path going around, so maybe I should. 4, 5, 6, 7, 8, 9. So my first blob has become a part of my partition, joining vertices 1. So that's one part. So that's just another way of drawing the first blob. Then these, So here, this vertex is by itself. So I have a part equal to 2. Then here I have two vertices together, and I guess, are they 4 and 5? So that's one other part. Then I have 6 by itself. And then, so these 3, which must be these 3, they are together in one part. No, it's 3. It's 3. Yeah, this one was already taken. So that's my last part. Okay, so it's certainly a partition. The non-crossing property is by planarity of this picture. And on now n plus 1 points, which are the vertices of this tree, you have Cn plus 1 non-crossing partitions. So that's a very direct way of generating, possibly at random, a map with a spanning tree. You build a tree with n edges, any tree. You choose a non-crossing partition, and from which you build those blobs that you contract into a vertex, and you have your object. So random generation of those things is easy. Now their asymptotic properties are still very mysterious. Well, not in terms of counting, but in terms of distances, for instance. Okay, so that was a very elegant way of counting maps with a spanning tree, or even 2 ways. The first one with a convolution formula, and this one which is combinatorially much more inventive. And now I want to show you a very clumsy way of doing the same thing. Not just because I like to be clumsy, but because this will tell us what to do when we want to look at, say, the Potts model on planar maps, or equivalently to count maps weighted by their Tud polynomial. So there was maybe a 1 or an A that was the elegant way, and so I come to a 2, which is the clumsy way. And the idea is that after having done all these nice combinatorics, we would like to be back to the very simple, down-to-earth things that Tud was doing. What happens if you delete the root edge? Or what happens usually if you contract the root edge? And the thing we'll use is the following. If I denote by, say, tau of m, the number of spanning trees of the map M. So really the series we want, and the series we've already determined, is the sum over all maps of T to the edge number times the number of their spanning trees. Okay? So it's a weighted enumeration of maps. Formally, we had a factor 1, and then we have the multiplicity of a given map, and by map I mean just a map without a tree, is the number of its spanning trees. You don't look happy, Laurent. Oh, well, that's the one that we have defined and obtained. So that's really the one we found. Okay? So that's what we've done. I'm just rewriting our former result. Okay, and the thing, so we are thinking of this contraction deletion of edges, and the thing we're going to use is the fact that given a map with some edge E, typically the root edge, well, maybe this root edge is not in the spanning tree. So what you really have is a spanning tree of the map from which you have removed the edge E. So I claim, so here that's when E is not in the tree. And that's the deletion by here, this notation, I mean the deletion of E. And you also have the trees that the spanning trees that contain the root edge. So something like that. And then you have a whole map around. So that's the tree. And so in this case, well, the number of spanning trees of M such that the root edge is in this tree is equal to the number of spanning trees such that this edge is contracted. So that's tau of M. So mind the notation. This is M in which I have contracted the edge E. And so this counts trees such that E is in the tree. Okay, so that's a simple recursive description of the number of spanning trees of the map. And we would like to combine this with our usual recursive description of maps to get a functional equation on the generating function S, typically. So there are some special cases which will be of interest. If E is a bridge or an isthmus, then when you delete it, well, you get two disconnected parts. So certainly you don't have any spanning tree. Oh, yeah. Thank you. Yeah. Don't like this notation so much. Thank you. And dually, if E is a loop, well, you can already complain that the contraction of the loop is not something well defined. And in fact, if it's a loop, there's no tree that can contain it. So what I've denoted that way, now like this, should be taken to be 0. Okay. Okay, so now we get back to our series, S of t, and we say, well, maybe we have again the atomic map, the map reduced to one vertex, which counts for 1. And then we have the sum for all maps of t to the edge number times the number of spanning trees of n minus e, where now I take e, the root edge, plus the number of spanning trees of m, where e is contracted. So I will write this 1 plus t, well, maybe S1 plus S2, S1 being this sum, and S2 the other one. Okay, so let me look at S1. So I have a map, and I have a spanning tree that does not contain the root edge. There's not. I should, so I'm always confused. Okay. So as we said before, if this root edge is a bridge, so now I want to relate this to the little pictures I used to do when I was just counting maps. And I have the case where the root is a bridge, and the case where it's not a bridge, where I have here smaller maps. Okay, so you remember these were the things in my first lecture. So let me look at S1. So I want E, the root edge. I don't want it in my tree. So maps that have a bridge as the root edge, they do not contribute at all in this weighted sum. So now I'm back here. And so I want, so S1, so that's the sum over, I call M prime, the map where I have deleted the root edge. So that's the bean. So it is weighted by its number of spanning trees. And then I want to get M from M prime, as in the unweighted case, which means that I have to start a new edge from the root corner and send it somewhere on one of the corners of the outer face. So this was the first method for counting maps. And this is the moment when we had to add a new parameter, namely the degree of the outer face, counted by a variable y. So we are going to have to do the same here for this case. And dually, we will have to introduce an additional statistics, the dual statistics, namely the degree of the root vertex, to encode this part by generating functions. So this means that, in fact, I'm going to consider now a 3-variable generating function. If I want to use this approach, contract, delete the root edge, which is the sum over all maps of t to the edge number, x to the degree of the root vertex, and y to, well, what I called the outer degree. I guess by symmetry, I should call it df, for degree of the root face. And then there's tau of m. So we need to enrich our enumeration by taking into account these two catalytic variables or catalytic parameters, which are dual of one another. Okay, so I return to this decomposition now, but carrying these two additional variables with me. So now S1 is some S1 of x and y and t. So as before, I tend to forget the dependence in t and denote this by just x and y. So I get back to finding S1. That is, I get back to this picture. And so I take some M prime, which has a certain outer degree D. So I want, so how should I write this? Sorry. So now I sum over all outer degrees D. I want to take a map M prime of outer degree D, so that's the coefficient of YD in my series. I will add an edge, the new edge, and then, well, so I create a new face, the degree of which ranges from, the new outer face has a degree ranging from 1 to D plus 1. This is what we had seen before. And then I should record the degree of the root vertex, which has increased by 1. And here, if you chew this for a moment, I should hear complaints that this is not correct. So this sum, I claim, corresponds to choosing to the various choices of my new root edge. Yeah, okay, so there's a problem here. Namely, so if I had my map M prime, and maybe it was not, the outer face was not simple, if I start my new root edge here and maybe here, the degree of the root vertex has not increased by 1, but by 2. So the weight I have given to such maps where the root edge is a loop is wrong. Okay, so I want to correct this. And so I go on here with my expression of S1. So what did I do? So if I have such a map, I say that it is, well, essentially two maps, each with a spanning tree and its own root corner that I glue, and then I make a loop around the first one. So having two pieces, I have a product of series. So in terms of the outer degree, only the second one will contribute, because the outer degree of the first one here is not part of the outer degree of the final map. And in terms of vertex degree, each one contributes. And then I have some factor x2. So that's the correct weight. And I have a y for this edge, which is in the outer face. So this would be the correct generating function, or the correct part of S1 corresponding to the case where the root edge is a loop. But I had also counted it here wrongly with a factor x. So what you should add is not x2, but x2 minus x to correct what we've done earlier. So to summarize this, and then there's a t. This S1, which was the sum over all maps having at least one edge of t to the edge number, x to the vertex degree, y to the face degree, times the number of spanning trees of m minus the root edge, is this, which we can write down as t, y, x, s of xy minus as a divided difference. So there's probably a y here. S of x1 over y minus 1 plus t x squared minus x y. So that's the usual term, the divided difference. But having now to take into account the degree of the root vertex, we have this correction term. In S, sorry. Yeah, so that's so that's the generating function of maps with outer degree D. Sorry? Series in X, I would say, yeah. So do I have all terms correct? Yeah. Okay, so that was S1, the contraction case. And then you have the dual case, sorry, the deletion case. You have the dual case, which will give and should give a symmetric expression . So by duality, S of xy is S of yx. That's an important property. And this is due to the fact that if you take a map with a spanning tree, then the dual tree is a spanning tree of the dual map, and you have exchanged the exponents of x and y. And so you have a second term. So either you argue by duality or you reprove the whole thing. Now, instead of having, now you want to contract your root edge. So it gives something like that. And then when you go backwards in the contraction description of Tutt's recurrence, so you essentially, what you have is you have your root vertex, and you have to decide how to split the incident half edges between edges to the right and to the left. So this will give, for instance, 1 and 3 remaining here. So this is how we explained in the dual setting this sum. Because when you do that, the degree of the root vertex now ranges from 1 to d plus 1. And here you want additionally to record how the degree of the outer face increases. And usually it will increase by 1 because you insert this new edge. But when you create a bridge, which may also happen, then it increases by 2. And that's the correction you have here. So it's completely dual. OK, so that's our equation. So S of xy is 1 plus what I denoted S1 plus S2. So we are in a situation that is similar but worse. Similar to but worse than what we had in the case of maps with no structure. Let me remind you that we had just one of these catalytic variables. We had one plus the case of the isthmus of the bridge. And then we had t, y, m of y minus m of 1 over y minus 1. So we had, so that's just for planar maps. So we had one of these divided differences in y. Now we have a difference in y and one in x. The equation is still, in a sense, quadratic, due here to these correction terms, either the loop or the isthmus construction. So it's globally quadratic, but if you look more closely, you see that in the main series, the one that has 3 variables, t, x, y, it's linear. That is, you don't have terms s of xy squared, and this will make our lives a bit easier. What else should I say? So you have this factor t all over the place, which means that underlying the functional equation is a recursion that allows you to compute the coefficient of Tn inductively. So certainly this equation, even though it involves S and specializations of it, it defines S uniquely as a power series in T. And what? How many minutes do I have left? 5 minutes. So. OK, and the reason why I did this very clumsy way is that, so I'll start with that next time, but I can still write the equation. So if instead of weighting maps by the number of spanning trees, we are going to weight them by what is called their TAT polynomial. Which is a 2-variable polynomial. So let me call it still tau m of 2 variables mu and nu. And that's a refinement of the number of spanning trees in the sense that for any map, or in fact graph or multigraph, if you evaluate the polynomial at 1, you get the number of spanning trees. So this I'll explain why it is equivalent to the so-called Potts model. And maybe the only thing I have to tell you about this polynomial is some recursive description of it. So I haven't defined it, but I do. And so in terms of properties, so if M has no edge, then tau m of mu and nu is 1, as it was for the number of spanning trees. If, say, E is an isthmus or a bridge, then tau m of nu is, so here I don't want to think, I want to copy whether it's mu or nu. So here it's a bridge, so I can contract it. And contraction, I denote it like that. And if E is a loop, then tau m is now nu times the third polynomial of the map where you have just deleted the loop. And then otherwise, you have a sum, as we had for the number of trees, that is tau m of mu. Mu is the sum of tau m of m minus e. So that's the deletion plus tau m contraction of mu and u. And so, well, that's probably a bad place to stop, but I don't want to start something new. So using, you can hopefully get a feeling of why this recursive description of the third polynomial is well suited to what we did here to count spanning trees. So we'll count separately the case of a bridge, the case of a loop, and then this will give rise to two sums, S1 and S2. Yeah. Sorry? There's a weight. You mean here the fact that there is a mu? Yeah, so it's essentially a weight on bridges and a weight on loops. You can think of it like that. So indeed, this is where this polynomial differs from the number of spanning trees. Namely, if you had a bridge, then Tm of 1, 1, or the number of tau m of 1, 1 is the number of spanning trees, and it's just equal to the number of trees of the map where you have deleted the loop. Rather, here you have an additional weight, and this is why it is a refinement of the number of spanning trees. Okay, and so we'll be able to write for the generating function of maps weighted by this two-variable polynomial an equation that is very similar to this one, but we won't do this today, just next time. Yeah.
So
No, no. And in general, it's sharp P hard to compute the third polynomial of a graph, except at some points for some values of mu and nu. 1, 1, among others. There's other. Okay, so do you have questions? Or? Okay, so I hope to see you next Monday.